Today I'm going to introduce a library called Rust Prometheus. And it's a simple library, but you will see how Rust makes this library safe and fast. So let me introduce myself first. I'm Wish, an infrastructure engineer from PingCap. You may already notice this name if you attend the lectures before. In PingCap, we mainly build two products. One is a distributed transactional SQL database called TiDB. It is written in Golang, and another one is a distributed transactional key value database called TiKV, written in Rust. And TiDB is just a SQL layer built upon the KV database. The key value database is the storage layer. And TiDB and TiKV have many customers worldwide, and we have adopted in banks, internet, enterprise companies for more than 15 gigabytes data. It's pretty large data, and these are all used in production cases. So let me introduce the architecture of our product. TiDB speaks MySQL protocol, and so your application can just use MySQL drivers to talk to him. And TiDB acts as a stateless SQL computing layer. And for the end layer, it is TiKV. It's a distributed KV storage. And this distributed KV storage is built in Rust. In PingCap, we also created and maintain a lot of many other Rust crates. For example, here the Rust Prometheus is the library I'm talking about today. And Rust RocksDB, it's a binding and wrapper for the RocksDB database. And Raft, it's an implementation for the Rust distributed consensus algorithm. And also gRPC. We built it to wrap the gRPC C language core to be high performance. And also, we built fail IS. It provides fail points. So what is Prometheus? Oops, sorry, not this one. It's just a system monitoring and a Latin toolkit. Here is a common flow of using the Prometheus. Usually, your application will collect matrix using a Prometheus client, and then you push the matrix to Prometheus or let Prometheus server pull your matrix. And finally, you will use some visualization tools, such as Grafana, to visualize the matrix you collected. And Rust Prometheus is just a Prometheus client. It is not a Prometheus implementation in Rust. Sorry for that, but I promise you that you will find many interesting things, even in this simple, small client library. So let's first get started and take a look at a small example of how to use this library. First of all, you need to define your matrix. There are many kinds of different matrix, like counter, histogram, and gauge, so on. Here, as the code demonstrates, we create a histogram matrix named HTTP request duration using the macro called register histogram vec. The histogram has one label called method. As you can see here in the fifth line, there is one label called method. So this is actually a histogram vector because for each value in the label, it will be different matrix. They are counted independently. So they are histogram vector. For the second step, you will record the matrix. As an example here, I just use random generators to generate this matrix. In real applications, you should use an instant to record the duration instead of what I did here. It's just for demonstration. Here the code simulates a request. As you can see, its duration will be randomized from 0 to 2. And its HTTP method will be from one of get, post, put, and delete. And we use this line, request duration dot with label values method dot observe duration to record this duration. It means that there is a request in a label specified where via the method variable takes a time specified by the duration variable. And finally, let's serve the matrix for the Prometheus server. There are two ways generally, the pull and the push. The code here provides a matrix service using the hyper library for Prometheus to pull matrix from. So here the code is pulling, but the Prometheus library also provides push functions. To pull a matrix, you just need a text encoder, as shown here. It's a text encoder new. And this text encoder will encode this gathered matrix to the output response. And the output response just look like this. So far, you have already collected your matrix to the Prometheus server, so it's time to visualize it. Here, I use Graphener to display the histogram using the Prometheus query language, as you can see in the blue text. Then you can see the graph here. Of course, you are feel free to use any kind of other visualization tools, but commonly, Graphener is a wise choice. So far, it looks normal. Just a simple matrix library provides matrix recording and encoding features. Next, we will see how Rust Prometheus library provides some unique features by utilizing some Rust advantages. First, Rust makes the library very safe. So why we care about safety? We use Rust Prometheus in our key value database, as you already know, TiKV, to record and report all kinds of metrics. There are hundreds of metrics. And safety is very critical for TiKV. For example, we don't want crashes. If TiKV crashed, your service is unavailable. Although TiKV is distributed and for the tolerance, but we want to minimize this possibility. We don't want to see that happen. So we want to eliminate crashes. And then, for the most important thing, we want to eliminate data corruption. As a key value database, it stores data permanently. So if there is a memory safety issue, normally the memory will be broken. For example, there may be garbages in the buffer that TiKV is going to flush to the disk or transfer to other peers. In this case, if this data is corrupted, it's horrible. It means that we will lose our data permanently. So we will not let it happen. That's why we very care about safety. So now let's begin our case study to see how Rust enables safety. Let me introduce some background. In the library, you can define and record labels for matrix vectors, just like this one. Here is the HTTP request, its method is post, its IP is on IP, and its path is /API. Then, after defining and recording this matrix, you will be able to query a matrix for a specific label. For example, you can know how many requests come from this IP address and how long it takes for requests to /API endpoint for 99% of requests. So as you can see, the label is pretty useful here. And in fact, in TiKV, we heavily use the label feature. When you're defining it, you use countervect. For example, I'm using a counter, so countervect new. And I provide 3 label names here. And when I record matrix, I use counter dot with label values and provide 3 label values here. Here is a restriction. So the number of labels you defined and the number of label values you provided, they must be the same number of values. Your label pairs must match. So how can we do that? Normally, we can just check the length at runtime. And if the length doesn't match, we can panic or throw errors. But this is very simple, but there are some disadvantages. For example, your code may be hidden in a branch so that your tests will not cover it. But you know, in production cases, all errors may happen. And that means if your test does not cover it, this error will be in production. It's very, I can't tolerate that. And also there will be runtime costs because you are just checking the length in runtime, so there will be runtime costs. So how can we fix that in a Rust way? We can use type systems to enforce label length. Here, I first declare a trait called label. Then I implement this label for different kind of string arrays. For example, I implement this label for an array contains 1 string and the array contains 2 strings and 3 strings. These types are all labels. Next, I will pass this type, this some type called some label type in the new function. I just pass some label type in the function and create a counter vec containing this type t. And for the recording pass, when we want to with label values, we also accept this t. So as you can see in the usage, if you pass an array with 2 strings, you will create a counter vec. Its t is string with 2 elements array, string array. And when you use this metric, you also need to pass a string, an array with 2 strings. If you want to pass an array with 1 string or 3 strings or other kind of strings, the compiler will reject your code. So in this way, you ensure that the label numbers you pass when you record the matrix is exactly the same when you created it, while you don't have to check its length at runtime. So it's both safe and fast. And for some improvements, we may also want these features. For example, we want to able to define the label using into string and using the label using as ref string. And also we may want n to be many values, for example, 4, 5, 6, 32. We want these many labels. And we don't want to repeat so many codes here. As you can see here, I repeat 3 lines for string length 1, 2, 3. And if we are going to create 62 labels, it will be a lot messy. So this is possible in Rust, but it's quite complicated. So I just paste a link here. You may refer to it later to see how it works. Here I demonstrate a code piece that uses this improved version. As you can see, when we create the counter, we can pass either a string reference or an owned string. It is into string. So if you are passing an owned string, there will be no cost. If you are passing a string reference, there will be string clones. That's what we expected because we will store these strings in a structure. So it must accept owned strings. But when we use the counter, it is as ref string. And as you can see here, also you can pass string references or owned strings. That's all fine. And the most fancy one is that if you define a matrix using owned string, you can also use it using a reference string. And if you define using a reference string, you can also use it in owned string. It's all fine. So also, it has all the features previously we taught, that is to ensure the length at compile time. So if you pass a string, pass an array only contains 1 string or 3 strings, it won't compile. There are some other cases in the Prometheus library. For example, we utilize send and sync markers in Rust. What is send and sync? For send, it means that a type can be sent to other threads. It is safe to send to other threads. And for sync, it means that the type can be shared for different threads. So, for example, considering thread local variables, it is not sent because if you hold a value in one thread, when you send it to another thread, the value no longer holds. So thread local variables is not sent. And we'll see an unsync example soon. And also we utilize must use attributes. Must use means that this type must be used. For example, in Rust, the result type must use. If you have a result type and you don't put it in a variable or don't call its method, the compiler will reject your code. And for example, in Rust Prometheus, we provide a timer that records elapsed time when it is dropped. So if you don't use it, it will be dropped immediately. And this is not normally developers may expect. Developers may expect this timer to run for the whole scope. So it is a must-use timer. Now let's see how Rust enables the Prometheus library to be very fast. Sorry, I made a mistake. It should be fast. So you see, I just copied. So why we care about performance? Because we record metrics very frequently. For example, we record a lot of metrics, for example, duration, scanned keys, skipped keys, and so on. And we have hundreds of metrics recording every second. And also, we record metrics for all operations TiKE provides. For example, get, put, scan, and so on. So the overhead of the matrix should be very minimal so that we can know what is happening without sacrificing the performance. Now let's study a case, which is a local unsync matrix. Normally, our matrix is a global matrix implemented using atomic variables, as you can see here. The advantage of using atomic variables is that it can be updated from everywhere, for example, multiple threads. But as you can see, for atomic variables, we need to use atomic operations to modify its value. For example, I use fetch add, and it's 10 nanoseconds on my laptop. And to improve that, we can introduce some local variables. So this is what local counter it is. So for local variables, they are not sync, and we can flush back to the global variable periodically. So you can both achieve, you can just achieve the speed while not meeting some data race issues. For example, you can just use x plus equal 1 to increase the local counter, and the counter will be flushed to a global counter, for example, every 2 seconds, 3 seconds, although it takes 10 nanoseconds, but it's fine because it only happens every 2 seconds one time. So in this way, it is very fast. And for a local counter, it is not sync because, you know, data race, if you create 2 threads, update the same counter, you won't get a final counter number you expect. It's a simple data race. And in Rust, it provides unsync marker to mark that this is not shareable for multiple threads. So the local counter is unsync. And by using this technique, we can both achieve fast and safe. You can use the local counter in a very fast way, and you will never abuse it. You will never share it in multiple threads. You will never use it in a wrong way. So it's both fast and safe. And let's study another case, which is caching matrix vectors. Oops. Also, let me introduce some backgrounds. As you may already know that matrix with different labels, they are counted independently. For example, here is a code created a countervec with 2 labels. And then I use the label, for example, I record with post slash, and record using get slash, and record using get slash API, and finally record using post slash. So post slash happens 2 times. So when we want to get its value, it should be 2. And for get slash API, only occurred 1 time. So when we get it, it should be only 1. And for other kind of label names, it should be 0. And of course, get slash is also 1. So as you can see, although it is the same matrix called the counters named name, but it has different label values. So actually, they are counted independently. So what happens inside the function with label values? It actually does these things. First, it will hash your labels. Here, it will just hash your post slash, and it will get U64. And then it will perform a hash map lookup. If you have already used this label value, the hash map entry exists, so it can just return it to you. And if this label value is fresh, you have not used it before, it will create a new entry. So it's just an atomic variable with 0 initialized. So as you can see, the with label values function actually does a lot of things. For example, hash, lookup, and also some branchings, and finally it returns the matrix. You may notice that there is a simple optimize. For example, instead of doing these things, which is accessing a counter, looking up a counter using get and slash API, and then increment it for the whole process, we repeat it for 100 times. Instead of doing this, actually, you can look up for only 1 time. So you look up 1 time, and then you increase it for 100 times. This is pretty fast. It's as fast as the case when you use the counter without any labels. So in TiKV, there are many service endpoints. For example, there are transaction get, transaction batch get, pre-write, commit, and so on. There are so many service endpoints. And we can use this piece of code to accelerate just in this way. We can write it manually to cache these labels. But you can see it is not dry at all. For example, here we have only 1 label called service. But what about there are 2 labels, service and status? As you can see, I should repeat, for example, transaction get success, transaction get fail, batch get success, batch get fail. It's a lot of code that even exceeds my screen. So how can we solve it? We can solve it using Rust macros, thanks to the powerful Rust. Yeah, I'm pretty a fan of Rust. As you can see in the code, this is a macro provided by the Rust Prometheus library. It's called make static matrix. And when using this macro, you can just provide your labels. For example, services, I give it these services, and for status, I give them this status, and it will take care of you. When you use it, it's pretty simple. You can just m.transactionGet.success. You will get a counter, and you can just increase it. So how is this macro actually implemented? It is pretty cool, right? But you may not know how it is written. So let me use some simplified example to illustrate how this, what happened to my laptop? Okay, that's fine. I can use some simplified cases to illustrate how this static metric macro is implemented. So let's take a look at some simple case. For example, we want some macros that expand these kind of things. We just want, after expanding, we can use it like this. For example, here is a counter we can with label values full, and this should be something that the macro expanded. And after expanding, I should be able to just increase the macro. And also we can just get a macro or some other functions. So the implementation is pretty simple. I can just create a struct called my static metric, and then it has two counters. When you new the struct, you can just cache the metric using counter with label values, just like what we did before. So this is the code we write, and this is what we expect. So our macro should expand the code in the left to the code in the right. But as you may know, in Rust Prometheus, there are more than one labels available. For example, you can supply 3 labels. For the first one, there are 2 values. For the second label, there are 3 values. And for the third one, there are 2 values. So in order to implement this kind of metric, actually you will need some more complicated codes, like the code shown in the right. For example, we want to access foo.user_a.success. So actually, you will need 3 structs. The first struct contains foo and bar for the inner 2, and for the inner 2, it contains 3 fields for the inner 3. And for the inner 3, it contains the actual counter. In this way, the declarative macros won't work because there are identified concat here. And also, you may notice that the logic, the repeat logic, is not the same for every labels. For example, for the first label and for the second label, it will expand to a struct we create. But for the third label, or let's say the final label, it will expand the code to some counter. So declarative macros won't work. Then let's use procedural macros. So what is procedural macros? Procedural macros allow creating syntax extension as execution of a function. For example, you can create function-like macros using procedural macros, and you can create derive macros. For example, here is the custom mod derive created by me, and you can derive this macro for your own type. And also you can use attribute macros. So to use the procedural macro, first you need to declare an entry in your cargo manifest file. It is stay inside the lib entry. So it's just a procedural macro equals to true. This indicates that your crate is a procedural macro, and the compiler will recognize it. Then you need to write a function. It's just accepts a parameter, which type is token string, and produce a token string. So it's just a transform function, setting a token string and transforming it and producing the new token string. For example, here I didn't write the body for the function. I just print the token string in debug mode. So you will see what token string it is. And remember that for procedural macros, you need to add this attribute, procedural macro for it, so that your function will be called when the macro is invoked. So let's see what will happen. In the left side, this is what our macro users will use. It's just write make matrix and pub struct my static metric full bar. You may notice that the syntax here is very similar to the Rust structure, but actually it's different because for full and bar, there are only names and no types. So actually it is an invalid syntax in Rust. It's just similar to a Rust structure. For the compiler output, you can see for this kind of code, it will generate these token strings. The first is identifier pub, the second is identifier struct, and the third is identifier my static metric, and then there is a brace group. And then here comes inside the group, there is an identifier full and comma punct, and then an identifier bar, and also a comma punct. So this is what your procedural macro function will get. Now you will write a function to transform these token strings into the token strings you want. So in order to do this, let's first parse it. Normally, we use a crate called sim to parse these tokens. For example, as you can see in the right, this is the sim parser implemented by ourselves. It's just called a metric definition. It contains visibility, that is the pub. If you don't write pub, its visibility is different. And it also needs information about the name you provided, and also a list of identifiers. It's just a list of label values you will provide. So here it should be full and bar. So this is the structure that we want to pass from these token strings. And then we will write the parser using the sim facilities. For example, the first, we just input.pass. We are passing a visibility. So we feed this visibility to the visibility variable. And then we will find a keyword called struct. So we also pass a token called struct. You may ask, what will happen if user doesn't provide some struct? For example, he may write pub enum. In this way, there is a question mark here and there are errors. So you can just get what you expected. And next, I expect here to be a name. So I also pass an identifier here. Finally, here is the brace. So I use the brace, the macro provided by sim. It will pass the brace. And the content inside the brace, as you can see, is just a list of identifiers concatenated by commas. So I can also use some facilities provided by sim. It is pass terminated, and token is comma. So it's comma concatenated. So, and token inside is an identifier. So finally, I will pass these tokens into some vectors. So I create an iterator and collect it into a vector. Let's see what it will happen. For example, I just wrote a parser and I will use it in this way. You can refer it to the sim documentation and you will learn more. Here I just demonstrate a simple use case. So in this way, it will pass the input token string using your metric definition parser and generate the structure you want. So here is the structure we passed from this input. As you can see, the visibility is pub, and the name is our my static metric, and there are two values, full and bar. So right now it's all fine. So for the final step, now we already know what user has supplied, and we want to reassemble the code, reassemble the token string to another token string. So here we can use a crate called code. For example, I want to reassemble the code for the yellow part. I want to resemble it. So I will write the code in the right. And the most important thing is this piece marked in yellow. As you can see, I just write code and visibility, struct, name, and values counter. And since here is a sharp and some brackets, so it's just a repeat list. So actually it will repeat every values and repeatedly produce these tokens. This is pretty, you can write it in a way that's much like source codes. As you can see, finally I will output this expanded token string. It's just like this. Although there are different space, for example, here there are new lines and there are no new lines, but you know it's fine. If we omit this space, you can see they are exactly the same what we want. Now, let's generate the rest part. It's implement my static metric. I want to transform token strings into this part. And so I naively write code like this. It's just, for example, the same repeat list. And inside the list, there is a double quote and sharp values and double quotes. And let's see what will happen. So in the compiler output, you will find something you are not expected. You'll find that with label values, its parameter is a string. So you are actually providing this string, right? And it's just to produce the string for you. So what's wrong with it? It's just because your values is an identifier, but here you want to produce a string. So you need to transform your identifier to the string, then it will work. So let's do it. Let's transform the identifier to the string. Here it is just a simple map. As you can see, data.values.iterator.map. Then, so I will get every identifiers. Now I will create a string literal using letstring new. In this string literal, I just copy the content without modifying it. And actually, you can modify the content. For example, you can concat or adding prefix or suffix, everything, whatever you want. It's just fine. So you can freely manipulate this identifier and create a string. And finally, we will use this sharp value string instead of sharp values to be here. So this sharp value string is a string, and it is not an identifier. So now it will work. This is pretty exactly the same what we want. We want the macro to generate this piece of code, and the macro will generate this piece of token strings. So it's exactly the same what we want. For more information, you can check out these two links. For our toy macro, you can check out this gist, and for the full implementation using Rust Prometheus, you can check out this link. It's a pretty complex implementation because the macro provided in Rust Prometheus provides many functionalities. It has a very complex syntax, and the syntax is very powerful. So to support all these kind of things, the macro itself is very long. But as you can see, the core idea is similar. You just first parse it and then manipulate it, and finally you will generate a new token string. So finally, let me talk about some future plans of this library. Currently, this library is not 1.0. It's just 0.5 or 6. I don't remember. But anyway, it's not 1.0. But we are planning for the 1.0 release. We will adapt it to the Rust 2018 edition, and also we will clean up its API because this code is written several years ago, and during these years, some functions of Prometheus has changed. For example, there is no product buffer anymore, so we will also remove the product buffer support. We will provide type-safe labels. So it's actually a prototype, but we will provide it. Also, we will provide some smaller library size, and maybe we will support the no standard library environment. and you can use it in WebAssembly or some embedded service. It's fine. And for the future, we will also support a metric kind called summary. And also, we continuously want to make the matrix very fast. So we have already got an idea. It's core local matrix, and we are still exploring how we can implement it. By using core local matrix, we are expected to have some greater performance. And also, we will provide some easier-to-use pooling handler and more to come. Contributions are appreciated. Thank you very much. You may ask some questions, but you know I'm not a native English speaker and I may not understand your accent quite well, so please speak slowly and so that I can understand it. I'm very sorry for that. I think maybe there are 2 questions. If there are more questions, you may ask me afterwards. Oh, so the type-safe labels is just, okay. He asked what type-safe labels is really is. So let me turn back. Here it is the type-safe labels. The type-safe means that the label numbers you provide when you define the matrix will be the same when you use it. It will be checked by the compiler instead of at runtime. So it's type-safe. When it is checked in the compiler time, and you don't need to worry about, for example, not being covered in tests or something else, and there is no runtime cost. And we are doing it in a type-safe way. So there's type-safe labels. Oh, yeah. He asked a question about whether it's possible to just switching off all of these things so that the performance can be greater. It's, of course, approachable, but this is not implemented. It can be approachable by using the macro, for example, config. You can configure a feature gate for this kind of things, and you hide it behind the config. So you can switch it on and or switch it off. And when you switch it off, the compiler will not generate these codes, so it will be no cost. Are there any other questions? Maybe one more? So you are asking questions about whether it is fast to use atomic variables? You mean other kind of approaches? Do you mean other kind of approaches? Okay, so let me show it here. Actually, we have benchmarked the performance of using atomic variables. Usually it takes 10 nanoseconds when you use an atomic variable in single-threaded environment. And when there are more threads, the condition may be worse because there may be cache contentions. And that's why we introduced local matrix. And also we found we are investigating this approach. It's a co-local matrix. This co-local matrix is also implemented using atomic variables, but it can avoid some cache contention. So in practical, it will be faster. But we are free to discuss some other implementations. We always want it to be very fast. Thank you.